In our last lesson, we looked at a relationship between sets based on the number of elements in the set, which we called cardinality. But what if sets look similar but don't have the same number of elements? In this lesson, we will explore this property in a bit more detail. Take a look at these two sets, A and B. Is there anything that you notice about these two sets? Did you notice that all of the elements in set B are also in set A? This is the special property that we want to discuss in this lesson. When every element of set A can be found within set B, we call A a subset of B. To show this, we use a long C shape and read it as A is a subset of B. Just like before, we can negate this statement using a slash. A is not a subset of B. Take a look at set A again. What we're going to do next is try to find all of the subsets of A. I'll help you out with the first two. The set containing the number 1 is a subset of A because all of the elements in this set are also in A. The set containing the numbers 1 and 2 is also a subset of A because 1 and 2 are inside of A. Take a moment and pause the video and see if you can find the rest of the subsets of A. Now in this case, since we're trying to find a lot of subsets, let's start trying to get things in a nice order. So first, let's list all of the subsets containing one number. And then from here, let's try to list all of the subsets containing 2 numbers. And then 3 numbers. And then 4 numbers. And I'm hoping that you found all of the following ones. There are a couple of ones that might have been overlooked. The first one that you might have overlooked is the full set A, 1, 2, 3, 4, 5. So this is the subset of all elements of A. It's also possible to take no elements from A and make a subset. This is the empty set. So now we have all possible subsets. There's a lot of them. Now here's where things can get a little bit crazy. We could take all of those possible subsets of a set and we can make a brand new set. A set that contains a bunch of sets. If we do this, the brand new set that we get is called the power set of the original one. So the power set from our last example would look like this. It's really big. Now the power set has a really cool property. Let's take a moment to find the power set of the set containing just one number, the number 1. So the power set's going to be a set that contains all possible subsets of A. So the power set will contain the empty set, as well as the set of all elements in this first case. Take a moment to try to find the power set of the set 1, 2. Here, our power set's going to contain 4 subsets. The empty set, the subset containing just the number 1, the subset containing just the number 2, and the subset containing all of the elements. What about the set 1, 2, 3? In this case, the power set should contain 8 subsets of our original set. Do you happen to notice a pattern with the power set? You may have noticed that powers of 2 are coming up. Our first power set had 2 elements, followed by 4 elements, which is 2 squared, followed by 8 elements, which is 2 to the power of 3. How many elements do you think would be in the power set for the set 1, 2, 3, 4? Or for the set 1, 2, 3, 4, 5? Well, for the set 1, 2, 3, 4, we expect the cardinality, or the number of subsets, to be 2 to the power of 4, which is 16 elements. And we've already seen the other set, 1, 2, 3, 4, 5, has 32 elements. Let's quickly chat about the main number sets we will work with in mathematics. The most fundamental set being the set of natural numbers. 1, 2, 3, 4, and so on. Sometimes 0 is included in this set, sometimes not. Sometimes the set might be called the set of whole numbers, and we use a fancy n to denote this set. Next up is the set of integers, which include all of the whole numbers, as well as their negative counterparts. Here we typically use a fancy z to denote this set, and the z stands for the German word Zahlen, which translates roughly to numbers. After the integers, we have the set of rational numbers. Here we use a fancy q to denote this set, which comes from the Italian word for quotient. The set of rational numbers includes all positive and negative fractions, and in this case we have to use set builder notation to describe the set. And we can read this as the set of all numbers of the form a over b, where a and b are integers and b is not equal to 0. We'll definitely return back to this definition a little bit later. The last major set we will use is the set of real numbers, which is denoted using a fancy R. This number set is the union of the rational numbers and the set of what we call irrational numbers. We're going to chat a bit more about irrational numbers later as well. There are other number sets which we might discuss too, such as the set of complex numbers or the set of quaternions. These topics would come up much later in mathematics courses and in physics as well. The reason for talking about these number sets is that they fit really nicely together as subsets of each other. Recall that the real numbers is really the largest set that we're going to be working with, so it's our outermost circle. The real numbers contains all of the rational numbers, as well as the irrational numbers. Now all of our integers are contained inside of the rational numbers. Our integers are just fractions where the denominator is equal to 1. And finally, we noted that all of our natural numbers are a part of the integers. So you can see how all of our number sets are nested together one inside of another. And as we progress in mathematics together, we'll try to revisit this diagram to fill in certain numbers and properties of each of these sets. All right, my little epsilons, stay positive.